categories of waves that we're going to talk about. Mechanical waves. Mechanical waves are waves like this, that have a medium that's disturbed, that starts oscillating, which makes the pieces next to it start oscillating, which makes the pieces next to it start oscillating. That's a mechanical wave. A mechanical wave requires a medium. It has to have a physical, actual entity to travel through. Another type of wave is an electromagnetic wave. Visible light is a type of electromagnetic wave. Radio waves are a type of electromagnetic wave. X-rays, microwaves. So electromagnetic waves, they have what we call an electric field portion and a magnetic field portion. We'll talk about electric fields and magnetic fields a little further in the semester. So this is a disturbance in the electricity and magnetism spectrum. Electromagnetic waves do not actually require a medium to travel. They can travel through a vacuum. They can travel through a medium, but they're not required to have a medium. Okay? That's why light from the sun can reach the earth. There's not a whole lot of stuff between the earth and the sun, but the sun, light gets to us. Conveniently for us, go ahead, sir.
Isn't light a particle itself?
Light can behave as a wave or as a particle. It can't do both at the same time. So, when we talk about the wave nature, it's a disturbance in the electromagnetic spectrum, but we'll talk about the particle nature of it as well. Once light actually hits something is when it behaves as a particle. As it travels from one point to another, it's behaving as a wave. And it will do things that all waves do. Okay. The third main type of wave that we'll talk about is a matter wave. A matter wave is the wave nature of a particle. So not only does light behave as a particle and a wave, but particles behave as particles and waves. Electrons, for example, have a wavelength associated with them. That's why you can use electron microscopes. It turns out the wavelength of an electron is smaller than the wavelength of light, which allows you to look at much smaller things. If you want, say you're into biology, you're looking at the cells of something. With light, you can see the cell as a whole, and the nucleus would be kind of a blob, but you can't see the other individual entities inside the cell. With an electron microscope, you can actually see inside the cell itself. You can see all the endoplasmic reticulum and the nucleus, and it's really cool. So electrons, protons, atoms. Technically, we have a wave nature as well, but we're so huge that it's not an obvious thing to see. We're going to talk about matter waves a little bit more in future chapters. So, kind of place this one on the back burner for now. We'll talk more about mechanical waves and electromagnetic waves first. So mechanical waves fall in two categories. Transverse and longitudinal. My favorite mechanical wave maker is a slinky. Works quite well. This slinky, though, is awfully huge, so I have to put it down on the floor to use it. So to make this work out nicely, would one of you mind holding the video camera so you can see it at the floor? And would one of you down here mind just holding on to the end? A transverse wave is one in which the medium itself moves back and forth while the wave travels along the length of the slinky. So this is a transverse wave. If I shake the slinky back and forth, the wave itself, that's the disturbance. The disturbance is what's traveling down from my hand to his. But the medium itself is moving back and forth relative to the direction the wave's traveling. Now, as I was saying before, the frequency is what I'm doing. I'm determining the frequency by how fast I'm shaking the slinky back and forth. I can change that frequency easily. I can shake it faster, or I can shake it slower. Notice the wavelength changes. When I shake it slow, the wavelength, the distance between peaks, is big. If I shake it fast, the distance between peaks is small. So there's an inverse relationship between the two. If wavelength's big, then the frequency's small. If wavelength's small, then the frequency's big. The second type of wave, the longitudinal wave, is when the medium moves parallel to the direction the wave's traveling. So I have to push and pull on the slinky. So you see parts where it's compressed together and parts where the slinky's further apart. The wavelength would be the distance from one compressed part to the next compressed part. Okay? And again, the faster I do it, it's harder to do it on longitudinal. The faster I do it, the closer together those compression parts get. Okay? Thank you. So transverse wave is when the medium moves back and forth while the wave travels along the straight line. So the medium moves perpendicular to the direction the wave's traveling. Longitudinal, the medium is moving parallel to the direction the wave's traveling. So as you push and pull on the slinky. Okay? So if the wave's traveling this way in a transverse wave, the medium's oscillating perpendicular to it. Now it could come in and out of the board too, that would still qualify as a transverse wave. In a longitudinal wave, if the wave is traveling this way, the medium is oscillating back and forth parallel to that. Now please keep in mind the medium as a whole is only oscillating. The end of the slinky didn't travel all the way down the length of the slinky and come back. It only oscillates back and forth. The wave travels all the way down the length of the slinky and comes back. But the medium just oscillates around a fixed point. A common example of a transverse wave that we're going to talk about is waves on a string. For example, musical instruments. If you play a guitar, you pluck the string. You created a disturbance. The wave travels on that string. Now those waves will travel extremely fast, which is why you don't see it actually physically travel down the length of the string and come back, because it's moving so quickly. Yeah.
Well, you can kind of see the vibrations when you're playing a lower note on, like, say, cello, bass, or viola.
Oh, certainly. You can see the overall vibrations. I'm just saying you wouldn't be able to see one piece of the disturbance travel down. But yeah, you can see it actually vibrate a little bit, definitely. Especially on the bigger strings.
So with like a vibrating string, so it's moving so fast that it looks like oscillatory motion is
pretty much
how it is, because it looks like it's just going up and down instead of
exactly
like that.
And it actually, we'll talk more about it in the next chapter, but we get interference is what's going on. Because waves, as waves go down and they reach a boundary, at least part of the wave always reflects back. And so the wave that's being created interferes with the wave coming back, which is what makes it look like that nice, looks like you're playing jump rope, basically. You get this nice big motion. It's moving so fast, though, that it's hard to see anything other than that big motion. An example of a longitudinal wave that we'll talk about is sound. So sound is longitudinal. What's happening, for example, when we talk, our vocal cords vibrate, which makes the air molecules vibrate, which makes the air molecules next to them vibrate, and so forth throughout the room until it gets to our ear. Those air molecules vibrate, which make our eardrum vibrate, which is then translated into sound for us. So sound is an example of a longitudinal wave. Earthquakes, for example, will produce both. The transverse waves of an earthquake, generated by an earthquake, move over the surface of the earth. It makes the earth vibrate up and down. But there are longitudinal waves that actually also go through the center of the earth and compress the material as it goes through. This actually, they use that to, that's how they've determined what the inside of the earth, how it's structured, basically, because of how those longitudinal waves move through the earth. Kind of an interesting thing. Electromagnetic waves are similar to transverse in that the electric field and magnetic field oscillate perpendicular to the direction the wave is traveling. So you can think of them as transverse. So another important piece of information then is what determines how fast these waves actually travel. Okay. With mechanical waves, the medium itself determines how fast a wave can travel. Sound, for example. If you've ever inhaled some helium and talked, so your voice sounds all high and funny, it's because the sound is traveling at a different speed through the helium than it did through normal air. It actually travels faster through helium. That's why you hear a higher pitch. Our book doesn't give us an equation for the speed of sound. It's actually pretty complicated because it's going to depend upon the density of the air, so it'll depend upon altitude, but it will also depend upon the temperature of the air, and it will depend upon the humidity. So it's a little complicated in terms of determining speed for sound. At whatever normal conditions they decided to state, I don't remember. It's around room temperature, I don't know what humidity. The speed of sound is around 343 meters per second. So 343 meters per second. It travels quite fast. We'll use this value for the speed of sound unless we're told otherwise. Unless the problem tells us that the speed on this particular day is traveling at 345 meters per second. Something different. Wave on a string. I forgot my other favorite wave maker. A telephone cord. I'll try to remember to bring it tomorrow. For anyone that has experience playing a stringed instrument, though, if you think about it, you can change the speed of the wave on the instrument by tightening those pegs, by changing the tension. So the speed of a wave on a string depends upon how tight that string is. The tighter it is, the faster the wave is going to travel. Okay? Basically, the tighter it is, a little oscillation in one piece of the medium is going to affect the next piece of the medium much more quickly, the tighter they're bound. The other thing that affects the speed of a wave on a string is how thick the string is. If you've ever seen a stringed instrument, not all strings are the same thickness. Some of them are really thin and some of them are really thick. The thin ones, the wave will travel faster at any one given tension than the thick ones. So the wave on a string, the speed of the wave on a string, depends upon the force of tension, Now your book uses capital T for tension, which is okay, except for we talk about period 2. And you don't want to accidentally try to figure out the speed of the wave from the period when it's supposed to be tension. So be careful. I'm going to write it as F sub T to remind us that it's the force of tension. And then it depends upon how thick the string is. Mu is called the linear mass density. It's how much mass per length of the string. So if you took a piece of the string that was 1 meter long, it's the mass of that 1 meter long section over the length of that, the 1 meter of that section. Thicker strings are going to have more mass for any one given length than thinner strings. So that's what the mu is for. So waves on a string depend upon the force of tension and the linear mass density. Speed of sound, we're going to use 343 meters per second, unless we're told otherwise. Electromagnetic waves. You've all seen Einstein's famous equation, E equals mc squared. C is the speed of light. That's the symbol we use for the speed of light in a vacuum. It's approximately 3 times 10 to the 8th meters per second. It's very, very fast. Okay, so C is V. As light goes from a vacuum into another medium, though, the speed is going to change. Just like these, if we change something about the medium, the tension or how thick it is, if we change something about the medium, that's going to change how fast this wave travels. This changes if we change the medium as well. The speed of light also changes if we change the medium. Okay. The speed of light in another medium is equal to the speed of light in the vacuum over what we call the index of refraction for the medium. So the index of refraction is something characteristic of your medium. So glass, for example, its index of refraction is approximately 1.5. Water is approximately 1.3. Okay. Index of refraction is something characteristic of the medium, so the speed of light will always decrease as light enters another medium. It slows down, which is why it bends, which is why we get like rainbows out of prisms and such. Other thing too that's kind of funky here is the index of refraction is different for different colors. That's why you get the prism if you shine it, a rainbow if you shine it through a prism. It's because N is actually different for red, orange, yellow, green, blue, violet, and so forth. Here's the time for the coolest equation of all that gets everyone in trouble. We have a relationship between the speed of the wave and its frequency. Okay. Remember shaking the slinky back and forth? The faster I shook it, those peaks were closer together. The slower I shook it, the peaks were farther apart. For all waves, the speed of the wave itself is equal to the wavelength times the frequency. Simplest, most wonderful equation ever. Easy, easy to use. But it totally fouls people up. If I increase frequency, let's say I have a string. If I increase the frequency, if I shake it back and forth faster, or even with the slinky, if I shook it back and forth faster, what does that do to the speed? It leaves it the same. Increasing frequency does not change the speed of the wave. That's why this equation causes people problems. What did increasing frequency do? It decreased wavelength. If frequency is big, wavelength is smaller, so that when you multiply the two together, you always get the same value for V. what do you have to do to change the speed? For example, the slinky. If I wanted to change the speed at which a wave traveled in the slinky, what would I have to do?
Change the speed.
I'd have to pull it tighter. I'd have to change something about the slinky. Exactly
So
right.
you have to think of velocity as a constant.
Exactly. For any one given wave, you have to think of velocity as a constant. Exactly right. In order to change the speed of the wave, you have to change something about the medium. If you have a string, you have to pull it tighter or make it looser. If you have sound, you need to change the temperature or change the material the sound's traveling through. If you have light, you need to pass the light through something different than a vacuum. If you want to change the speed of a wave, you must change the medium.
Isn't that why Maxwell called C? C is for constant.
It might be, I'm not sure, but it would make sense. Yeah. So, beautiful equation, we'll use it quite a few times, but please keep in mind, if you change wavelength and frequency without changing the medium itself, you're not going to change the speed. So you have to think of the speed as a constant value for any one given medium. If you change the tension or you change something about the medium, then the speed will change, but that brings us back to these equations. Okay?
So the medium is the only thing that can change the wavelength, not what you're plugging.
No, it can only change the speed of the
I mean,
wave.
The speed.
Correct.
Yeah. And so it doesn't matter what you're plugging it with or anything like that.
No, the speed of the wave doesn't matter how you're plucking it, how fast you're shaking it. Exactly. The medium itself will determine how fast it travels. That's exactly right.
What if the wave destroys the medium?
What if the wave destroys the
Or
medium? Then
modifies the medium. We'll say, put it that way.
you,
Say you pluck a string so hard that it throws off the tension.
then that will change the speed, yes. Yeah, if you pull it hard enough to change the tension, then yes, you've changed the medium, and that will change the speed.
So changing tension changes medium.
Changes, yeah. So the medium properties, for example, on a string, tension determines how fast. So if you change the tension, it'll change how fast it goes.
I was gonna say, so, no matter what medium you're using, if you have the same wavelength, you have the same frequency.
Yes. So any one given medium, one wavelength will correspond to one specific frequency. Exactly right.